These are the answers to homework 4E. Question number 1. For the decomposition of ammonia, the following data was measured. At times of 0, 1 second, and 2 seconds, the concentrations of the ammonia were 2.000 molar, 1.993 molar, and 1.987 molar. For this first order reaction, write the rate expression and calculate the rate constant K. So if you're told it's a first order reaction, that means that the rate law would be rate equals K multiplied by the concentration of NH3 to the first power. To calculate the numerical value of the rate constant, we can't use this rate law because we don't have any rate data. But what we can do is we can take the concentration and time data and use that. If you have first order kinetics, then concentration and time create a straight line graph if you plot the natural log of concentration versus time. And they're related through this equality statement for first order kinetics. The natural log of the concentration of NH3 at time t equals negative KT plus the natural log of the concentration of ammonia initially. So if we assume at time 0 that the initial concentration of ammonia is 2.000, I can pick either 1 second or 2 seconds for the time t and put in the corresponding concentration of NH3 at that particular time. If I do that, then what I have circled here is going to be the slope of the line because this fits the equation y equals mx plus b. So if I can calculate the slope by going difference in y's over difference in x's, that will equal negative k. And if I take the negative of the slope, that will be k. So the slope is going to be the difference in the y's, so the natural log of 2.000 minus the natural log of 1.987, which was the molarity of the ammonia at 2 seconds, and then divided by the difference in x's, which are the time values, 0 minus 2. And this comes out negative 0.0032 with a guard digit 6 seconds to the minus 1. So that's the slope of this particular linear equation. Because the slope equals negative k, that means that negative k equals negative 0.00326 seconds to the minus 1. So therefore, dividing both sides by negative 1, k equals 0.00326. And because the answer should be two significant figures based upon the subtraction in the numerator, then the answer comes out 0.0033 seconds to the minus 1. Now, recognizing this is a linear relationship, you can actually use all three data points in your calculation if you use Excel. And if you on Excel plug in the three different time values, 0, 1, and 2, take the natural log of the three different concentrations and ask it to sketch a graph for you and display the equation on the graph itself, you can see that on the graph it says y equals negative 0.0033x plus 0.6931. The slope is negative 0.0033, and because the slope is negative k, that means that graphically from Excel, k would be again 0.0033 seconds to the minus 1. Number 2, the reaction of SO2-Cl2 decomposing into SO2 and Cl2 is a first order reaction, and the rate constant is 2.2 times 10 to the minus 5th seconds to the minus 1 at 320 degrees Celsius. What fraction of SO2-Cl2 is decomposed on heating at 320 degrees Celsius for 90.0 minutes? So in problem number 2, they're telling you it's a first order reaction. That means the rate of the reaction equals K multiplied by the concentration of SO2-Cl2 to the first power. And if it's a first order reaction with respect to SO2-Cl2, then we can write an equality statement that must be true for any first order reaction, and that would be the natural log of the concentration of the reactant at time t will equal negative KT plus the natural log of the initial concentration of the particular reactant. So they're asking you what fraction of SO2-Cl2 is decomposed upon heating for 90 minutes. We know the value for K. They told us the specific rate constant was 2.2 times 10 to the minus 5th seconds to the minus 1. T is how long the reaction's been progressing. That's going to be the 90.0 minutes. And if my constant is in seconds to the minus 1 and my time is in minutes, the units won't cancel out. So the 90.0 minutes are going to have to be switched to seconds, but at least have a value for both K and for T. In order to solve for the fraction of SO2-Cl2 that's decomposed upon heating, then I'm going to have to make up a value for the initial amount of SO2-Cl2, and I'm going to make up 1 molar for that. And in fact, what you can do if you'd rather not do it in terms of molarities, you can do it in terms of moles, and we'll see this later on in the homework, that as long as the amounts of the reactant are proportional to their molarities, then you can do moles of each, you can do grams of each, you can do molarities of each. And so I'm going to make up a number of moles of SO2Cl2 that are initially in the container. I'm going to say 1.00 moles of SO2Cl2. So I've got all the values for the right side of my equation. The K value, 2.2 times 10 to the minus fifth seconds to the minus 1. My time switched to seconds is 5,400 seconds. And then the natural log of, and this is what I'm making up, I'm going to say initially I'm going to start with 1.00 mole of the SO2Cl2. Well, we can now solve this for the moles of SO2Cl2 at time t. And if you actually calculate everything on the right side of the equation, that becomes negative 0.119. Then if you raise the entire equation to E as a base, you can solve for the SO2Cl2, which is going to turn out to be 0.89. So if you started with 1.00 moles of SO2Cl2, this is telling you that after 90 minutes, you're going to have 0.89 moles of SO2Cl2. So they want to know, in this particular problem, what fraction of it decomposes. So the 0.89 out of the 1.00 is the amount that doesn't decompose. So the amount that does decompose is 0.11 moles, and the fraction will be 0.11 moles decomposes out of the original 1 mole, turns out to be a fraction of 0.11. You could say 11/100ths, or in a percent form, that would be 11%. Number 3, given the following data for the reaction trans C2H2Cl2 turning into 6 cis C2H2Cl2, and that data looks like this, A says, what is the order of the reaction? So when you're given data for the amount of a reactant and how long the reactant's been proceeding, the only way you can do this is by trial and error and testing to see if the reaction is either 0 order, 1st order, or 2nd order in the trans C2H2Cl2. So to test for 0 order, we know you'd get a linear plot if you graph the concentration of the reactant versus time, or moles of the reactant versus time, and we've got moles in this problem, so I'm going to do that. So to test to see if it's a linear plot, I'm going to figure out the slope between the first 2 points, the slope between the 3rd and 4th points, and see if they're consistent. So for a linear plot of concentration of C2H2Cl2 versus time, the numerator would be the difference in the moles of C2H2Cl2, so 1.00 mole minus 0.90 moles, divided by the time difference, 0 minus 10, and that comes out negative 0.010 moles minutes to the minus 1. If I do the same thing and determine the slope between the 3rd and 4th points, in the numerator, difference in y's would be 0.81 moles minus 0.73 moles. The denominator, 20 minus 30, this comes out negative 0.008 moles per minute, and these slopes are not constant, so therefore this reaction is not 0 order. Next, we're going to test for 1st order. And if you have a 1st order relationship in your rate law, that means that a linear plot would wind up being the natural log of the reactant versus time, or the natural log of the moles of the reactant versus time. And so to do this, same thing, it's just I'm going to do difference in y's as the natural log of the moles of the reactant minus the natural log of the moles of the reactant. So for the first 2 points, it's natural log of 1 mole minus natural log of 0.9 moles divided by 0 minus 10. This turns out to only have the units of minutes to the minus 1, and it comes out negative 0.0105. Between the 3rd and 4th points, natural log of 0.81 minus natural log of 0.73 over 20 minus 30. This comes out negative 0.0104 minutes to the minus 1. In terms of significant figures, these both seem pretty close to each other, but unfortunately, I don't know, that's a little bit iffy. I sort of gave you this one on purpose so you wouldn't know for sure if it really was 1st order, so you're going to have to go ahead and test 2nd order, because maybe it's 1st order, but I don't know, maybe the 2nd order test will come out more close than these two. So let's test for 2nd order. If this is a 2nd order reaction, then the reciprocal of the concentration of the reactant versus time will wind up giving a straight line. So for the first 2 points, 1 over 1 mole minus 1 over 0.9 moles divided by 0 minus 10 gives me a slope of 0.0111 moles to the negative 1 minutes to the negative 1. For the third and fourth points, 1 over 0.81 minus 1 over 0.73 divided by 20 minus 30 gives me a slope of 0.0135 moles to the minus 1 minutes to the minus 1. These are definitely not the same, so therefore it's not second order. So out of the 3 tests I did, 0, first, and second, the data that gave me closest to the same slope for the points I tested was the first order. So therefore we can conclude that this reaction must be first order with respect to the trans C2H2Cl2. B says, predict the quantity of the trans compound after 50 minutes. So now that we know that it's first order, we know an equality statement that's always true for first order kinetics. And for this particular reactant, it's going to be the natural log of the concentration of the reactant is going to equal negative KT plus the natural log of the initial concentration of the reactant. So they said predict the quantity of the trans compound after 50 minutes. So how much will we have after 50 minutes? Well, we need to know K, we need to know T, and then the initial concentration, we're going to do the natural log of the initial concentration to the end there. That's going to be my value at time of 0, and we're going to use 1.00 moles for that. So I'm going to do this in terms of moles. Now, the slope, you notice from the equation above, is negative K. And we actually figured out the slope in our part A of the problem. So the slope was negative 0.0105 minutes to the minus 1. So if the slope equals negative K, that means we know what K is. Divide both sides by negative 1. K must be 0.0105 minutes to the minus 1. So we know K. The decay time is 50 minutes. I know that. And then I'm going to go natural log of 1.00 moles in this case because that's the quantity you had at time 0. So we know the constant. And in this equation, if we do this in terms of moles, then I'm going to put in my K value, 0.0105 minutes to the minus 1, the decay time of 50 minutes, and add to it the natural log of the number of moles of the C2H2Cl2 at time 0, which was 1 mole. And now we can just solve for the natural log of the concentration of the reactant at time t. Turns out to be negative 0.525. And if I raise both sides of the equation to E as a base, I can solve for the moles of C2H2Cl2 at time t, and that turns out to be 0.59 moles. So that means that after 50 minutes, the 1 mole of the reactant reacts away so that you only have 0.59 moles left after the 50-minute time frame. C says, how long will it take half of the trans compound to decompose? So to do this, you're going to wind up making up a number here. If we take this equation, and we know that the initial amount of moles of the reactant are 1.00 moles. If we're trying to solve for the time it takes for half of it to react away, T is the variable, but on the left side of the equation, the moles of C2H2Cl2 at time T has to be half the original amount. That value is going to be 0.50 moles. So to calculate a half-life, you just have to take the initial number of moles, whatever they are. In this case, it was 1.00. And then for the amount of moles of the substance at time t, put in half of that, 0.50. We still know the constant K, 0.0105 minutes to the minus 1. So you're solving for the amount of time it takes for the 1 mole to decrease to 0.5 moles, which we call the half-life. So natural log of 1 is 0. Natural log of 0.50 is negative 0.693. If I want to solve this now for x, I would divide by the negative 0.0105 minutes to the minus 1. Actually, I'm going to multiply through by just negative 1 first, so now I have all positives. Then I can divide by 0.0105 minutes to the minus 1, and I get my value for x, which turns out to be 66 minutes. And so therefore, we can determine that the half-life for this reaction is 66 minutes. So a half-life is a typical thing you can calculate for a chemical reaction, much like we've calculated half-lives for radioisotopes as well. Number 4, given the following data for the reaction of 2NO2 going to N2O4, A, what is the order of this reaction? So once again, with this kind of data, molarities and times, we have to do this by trial and error and test 0 order, first order, and second order by knowing which one of those orders gives particular linear graphs. So we know for 0 order, a plot that would be linear would be concentration of the reactant versus time. So I'm going to pick 2 random points, the first 2, and go difference in y's over difference in x's, and get a slope between those 2 points. It comes out negative 0.00484 molar minutes to the minus 1. Now I've got to pick 2 other points. It doesn't matter which ones you do. I'm going to wind up picking the 4th and 5th points, but you could have picked the 3rd and the 5th, or the 2nd and the 4th, as long as it's not the 1st and 2nd again. But pick 2 other points, difference in y's over difference in x's, and calculate the slope. It comes out negative 0.0016 molar per minute. These are not the same, so we can therefore conclude that it's not 0 order with respect to NO2. To test for first order, we know that would create a linear graph if you plotted the natural log of the reactant's concentration versus time. So if I take the first 2 points again, natural log of 0.556 minus natural log of 0.435 divided by 0 minus 25, that'll give me just the units of minutes to the minus 1. And I get negative 0.00982 minutes to the minus 1. And then again, pick 2 other random points, and I'm just going to pick the 4th and the 5th ones. Natural log of the concentrations over the difference in times, and this turns out to give us a slope of negative 0.00566 minutes to the minus 1. These 2 numbers definitely are not the same, and so because they are not the same, this would not be first order. It better be second order then, so let's do the test for that. The test for second order is you get a linear plot if you graph the reciprocal of the concentration of the reactant versus time. So for the first 2 points, I'll go 1 over 0.556 molar minus 1 over 0.435 molar divided by difference in times. And I wind up getting minutes to the minus 1, molar to the minus 1, with a value for my slope of 0.0200. If I pick the 4th and 5th points, reciprocal of the concentrations subtracted, and then divided by the time frames, 75 minus 100. And in this case, I get 0.0201 molar to the minus 1 minutes to the minus 1. Just significant figures of the exact same number, a little bit different because of experimental data in the guard digit. But these are definitely the slopes that are the most consistent. And so that means the only explanation would be that this reaction has to be second order with respect to NO2. B says predict the concentration of NO2 after 200 minutes. So now that we know it's second order, we will use the equation that relates second order, the equality statement for second order. And that equality statement was, for second order kinetics, 1 over the concentration of the reactant at time t will equal K times T plus 1 over the initial concentration of the reactant. So it's important to know what order the reactant is before you get the equality statement. You have to match the correct one. In this case, we're going to know what the K value is because in this equation, y equals mx plus b, K exactly equals the slope. So what we had just calculated is the slope between any sets of points. That's our value for K. And that value we saw was 0.0200 molar to the minus 1 minutes to the minus 1. They said you want the reaction to go for 200 minutes. Your value for T is 200 minutes. Then what's the initial amount? The amount of NO2 initially, that's at time 0. It's 0.556 molar, so we plug that into the very right side of the equation. So I'll be able to solve for the reciprocal of the concentration of NO2 at time t by going 0.020 times 200, then adding 1 over 0.556. If I add up the entire right side of the equation, it comes out to be 5.8 molar to the minus 1. So that equals the reciprocal of the NO2 concentration. If I take the reciprocal of both sides of this equation, I'll get the concentration of NO2 at time t equals 0.17 molar, and that's going to be the concentration of the NO2 after the reaction is run for 200 minutes.